Good afternoon, everyone. I welcome you all to this next lecture of Dynamics of Machine. As we were discussing the topic of friction. Okay. In friction, we have to study majorly under two broad topics. First is the bearing, and second is the clutches. Okay. So we started with the bearings, and we saw how the frictional loss is happening in the bearing. So let's quickly discuss what we did in the previous class. From the starting, we have discussed that there are two theories which are very close to the practical, which we apply in order to find out the power loss due to friction. So the first theory was the uniform pressure theory, and second theory was the uniform wear theory. Okay, so we did footstep bearing, which is also known as uh, flat pivot bearing. Then we did the conical pivot bearing. So in the previous class, we saw conical pivot bearing. So let's just have a quick recapitulation of what we did in the previous class. Okay. So we saw the conical pivot bearing, and this was the diagram which we used to understand uh, uh, the condition. Okay. So W is the capital W. This is the load or the axial thrust which is coming on the shaft, and that the shaft has to transmit to the bearing. R is the radius of the bearing, capital R. Now this conical surface has the slant height of L, and the pressure which is acting, the normal pressure which is acting perpendicular to this conical surface is denoted by Pn. Okay, and this included angle, that is 2 alpha, and alpha would be the semi-cone angle. Okay, mu is the coefficient of friction, and so on. So at a radius r, we took a small element having thickness dr. All right, and the slant height of this dr thickness element is dl. Okay, now this, by the help of geometry, we saw that dl is equals to dr cosec alpha. Okay, and area of this ring would be 2 pi r dr cosec alpha, right? Now first we saw the uniform pressure theory. In uniform pressure theory, the uh, this normal load acting on the ring was denoted by del wn, and it would be normal pressure into area. So it came out like this. Now what would be the vertical load acting on the ring? So it would be the sine component of this normal load. See, del wn would be acting in the direction of pn itself. So it will have our vertical component, and that vertical component will be in terms of sine alpha. So this del W would be equals to del Wn sine alpha, right? Now, this vertical component uh, is further resolved, and we get del W is equals to Pn 2 pi r dr. Okay. Now, in order to calculate the total vertical load, we'll integrate this del W from 0 to r, and we find that it comes out to be pi r square into Pn. So from here, we can determine the value of Pn. So Pn is equals to W upon pi r square. Okay. Now we have the normal load. So now we can calculate the frictional force. So the frictional force which would be coefficient of friction multiplied by this del Wn. So it comes out to be 2 pi mu Pn cosec alpha into r into dr. Okay. And once we have frictional force, we can easily determine the frictional torque. Frictional torque will be Fr into r, this Fr acting at a radius r. Okay, so by resolving it, we got it as frictional torque acting on the ring, elemental ring. It came out to be 2 pi mu Pn cosec alpha r square into dr. So this much amount of torque was acting on the was acting on the elemental surface. So in order to get the frictional torque on the entire bearing surface, we have to integrate this from 0 to r. So again integrating it, and finally we reached to an expression that frictional torque is equals to 2 by 3 mu into W into R into cosec alpha. Now from the geometry we can see that this R cosec alpha would be equals to the slant height of the cone. Okay, so this can be written as total frictional torque is 2 by 3 mu into W into L. So this is the expression we obtained for the case of uniform pressure theory. Now, again, we saw according to uniform wear theory, this PR into R would come out to be constant. This we have to assume. Okay, so this PR is equals to C by R. Now, this del W would be pressure multiplied by the area of the ring. So it comes out to be PR into 2 pi R dr. We'll substitute this value of PR and we'll get del W is equals to 2 pi C into dr. So this is the amount of load acting on the elemental ring. In order to calculate the load acting on the whole surface, we will integrate it from 0 to R, and this comes out to be 2 pi C into R. Okay. Now this C is equals to W into 2 pi R. Okay. Now the torque which is acting on the elemental ring, this would be 2 pi mu PR into cosec alpha R square dr, and we will, and this is the amount of torque, frictional torque acting on the elemental ring. So we'll integrate this from 0 to R in order to get the frictional torque acting on the whole surface. So once we integrate this and substitute the value of C and simplify it, we got frictional torque is equals to 1 by 2 mu into W into R cosec alpha. Again, this R cosec alpha would be equals to L. So this is the expression we obtain for frictional torque in case of uniform wear theory for conical pivot bearing. Okay. Also in the previous class, we compared this equation by conical pivot bearing, by flat pivot bearing. And we saw that the only difference is we have to multiply it by the term cosec alpha in case of conical pivot bearing. Here also, according to uniform pressure theory, this extra term of cosec alpha comes into the picture. Okay, so this all we discussed in the previous class. I hope you remember this and understood this clearly. Now let's begin with today's class. In today's class, we'll be discussing about the flat collar bearing. Okay, now this flat collar, as we discussed in the introductory class, that this collar is the integral part of the shaft. And this collar, what is the function of this collar? This collar will be resting on the bearing, and all the axial thrust which is coming on the shaft will be transmitted to the bearing by the by means of this collar. Okay, so obviously there will be a radius of the collar which is taken as R1. Okay, and this R1 is the external radius of the collar and R2 is the internal radius of the collar, and the internal radius of the collar is equals to the radius of the shaft. Okay, so R1 and R2 are the internal and external radius of the collar. Okay, so obviously the area, if you see in the top view, the area of the collar would be looking something like this. Okay, there will be two concentric circles, and the area would be the uh, that is the area which is required to us would be the area between these two circles. Okay, so the outer radius is R1 and inner radius is R2. So this hatched portion area would be pi R1 square minus R2 square as written over here. Okay. Now, in order to arrive to the equation of torsional frictional torque, again we will consider a small elemental ring at a radius R, and that elemental ring has a thickness of dr. So again, its area of this elemental ring will come out to be 2 pi r into dr. Okay. Now, this is a single collar shaft. In case we have a huge amount of axial load, axial thrust coming on the shaft, and that has to be transmitted to the bearing, then we can use multiple collar also. Okay, all the collars would be of equal size, and they all will have external radius as R1 and internal radius as R2. Okay, so for multicollar also, the equation will be very similar. Just the n will be multiplied. N, which is equals to number of collars, will be multiplied in the formula. Okay, so first let's consider this single collar shaft and derive the expression for frictional torque. Okay, also these Flat collar bearings are also called as thrust bearing. Okay, and in figure A and B, single collar and multi collar bearings are shown. All right. So let's move on to the derivation. Let's consider first the uniform pressure theory, and according to uniform pressure theory, we'll determine this pressure is pressure which would be equals to load upon area. So load, which is axial thrust, is W, and A is area. So pressure comes out to be W upon pi R1 square minus R2 square. Okay. Now in the flat collar bearing, we already derived the friction. We already derived the expression for this frictional torque, which is acting on the elemental ring. Okay. So this expression we have taken from here, from there itself. So if you are unable to comprehend this, just visit the derivation of flat pivot bearing, and you will be able to understand how this expression was derived. Okay. So this TR would be equals to 2 pi mu P into R square dr. Okay. So this load would be multiplied by the radius r, and that we will arrive to this equation. Okay, now in order to get uh, the frictional torque in the entire surface of the collar, we'll integrate it from R2 to R1. Okay, so previously we always had the upper and lower limit as R and 0, but in this case, only surface which is coming into the contact of the bearing is this collar. Okay, so we have to determine the uh, frictional torque which is acting on this collar. Okay, so the upper and lower limit will be R1 and R2 respectively. So we'll integrate this equation, and we'll arrive to this equation by resolving it. That uh, okay, this 2 pi mu P R1 cube minus R2 cube by 3. Why? Because this R square, once you integrate it, it will become R cube by 3, and you substitute the limits. So you will get 2 pi mu P R1 cube minus R2 cube by 3. Okay. Now we'll substitute the value of W. We'll substitute the value of P over here, and P is equals to W upon pi R1 square minus R2 square. So this will substitute, and we'll finally arrive to the expression for frictional torque. Total frictional torque is equals to 2 by 3 mu into W R1 cube minus R2 cube upon R1 square minus R2 square. Okay, so this is the equation for total frictional torque in case of collar bearing or thrust bearing, considering uniform pressure theory. Okay, so I hope this is clear to you. Now this can be written as 2 by 3 mu into W into R. Sorry, R effective, and that effective radius we can substitute as R1 cube minus R2 cube upon R1 square minus R2 square. Okay, so in previous cases we saw that in case of conical pivot bearing, or in case of uh, this other bearings, we saw that it was 2 by 3 mu into W into R. Okay, so only this initial portion is similar. Only the effective radius which is employed over here is R1 cube minus R2 cube upon R1 square minus R2 square. Okay, so this is the expression for frictional torque in case of uh, thrust bearing for considering uniform pressure theory. Okay, now let's move on to uniform wear theory. All right. So again, considering uniform wear theory, uh, as we have seen previously, that the load transmitted on the ring, considering uniform wear, is this del W is equals to PR multiplied by 2 pi R dr. Okay, and this PR into R used to be constant, and this PR is equals to C upon R. So we have substituted this, and it comes out to be 2 pi C into dr. Okay, now in order to get the total load, we will integrate it from again. Please make sure that you keep the limits as R1 and R2. Okay, so this W becomes 2 pi C R1 minus R2, and this C would be equals to W upon 2 pi R1 minus R2. Now this frictional torque acting on the elemental ring would be mu multiplied by del W into R. So it comes out to it 2 pi mu C into R into dr. Now for total frictional torque, we will integrate this equation and put the limits as R1 and R2. Okay, So once you integrate it, this r will become r square by 2. And once you substitute the limits, it will be 2 pi mu c r1 square minus r2 square divided by 2. Okay. Now this becomes t is equals to 2 pi, t is equals to pi into mu into c r1 square minus r2 square. Okay. And this, once we substitute the value of c, that is equals to w upon 2 pi r1 minus r2. Okay. We derive to a equation. See, this r1 square minus r2 square can be written as r1 plus r2 multiplied by r1 minus r2. So that r1 minus r2 would be get cancelled, and we'll arrive to this equation that total frictional torque is equals to 1 by 2 mu into w into r1 plus r2. Okay. So this will be the expression for total frictional torque for thrust bearing according to uniform wear theory. So according to uniform pressure theory, it was coming out to be 2 by 3 mu into w r1 cube minus r2 cube upon r1 square minus r2 square. And according to uniform wear theory, we have 1 by 2 mu into w r1 plus r2. Okay, so I hope this is clear to you. Now let's move forward and do some numericals. All right. So let's see the numerical. So a conical pivot bearing is given to us, and it supports a vertical shaft of 200 diameter. So the diameter of the shaft is given as 200 So the radius would be 100 right? It is subjected to a load of 30 kilonewton. So the uh, W is given to us. The angle of cone is 120 degree. See, this angle of cone is given as 120 degree. It is not mentioned that it is semicone angle. So we have to take this 2 alpha is equals to 120 degree, right? So alpha would be 120 by 2, that is 60 degree. Okay. And the coefficient of friction is 0.025. All right. This coefficient of friction value of mu is given to us. Okay. Now what we have to find is the power loss in the friction when the speed is 140 rpm. So the value of n is given to us as 140 rpm. Now this power loss in the friction is to be determined assuming uniform pressure theory and uniform wear theory. Okay. So let's see how it is to be solved. First, we will write the given data. So D is equals to 200 So R will become 100 or 0.1 meter. W is equals to 30 kilonewton. We'll write it in terms of Newton. 2 alpha is 120 degree. So alpha will become 60 degree. Now this mu is equals to 0.025. This is given. N is 140 RPM. So it is converted into omega by 2 pi n by 60. So omega comes out to be 14.66 radians per second. Why do we need this? Because we want to calculate the power, and power is equals to t multiplied by omega. Okay, or you can write this omega as 2 pi n divided by 60. So the power becomes 2 pi nt by 60. Okay. Now, first, assuming uniform pressure theory, so we have to calculate the power. So for that, we need to calculate the frictional torque. And we know for conical pivot bearing, assuming uniform pressure theory, the torque is equals to 2 by 3 mu into W into R cosec alpha. Okay. So we have all the values. We have mu, we have W, we have R, and we have value of alpha. So by substituting that and solving it, we get frictional torque, value of frictional torque as 57.7 Newton meter. And we have the frictional torque and we have the value of omega. We can easily find out the power. And once we do that, we find this power comes out to be 846 watts as per uniform pressure theory. Okay. Now, in question, it is given that we have to find it out according to uniform wear theory also. Okay. So we have frictional torque for conical pivot bearing according to uniform wear theory is 1 by 2 mu into W into R cosec alpha. Okay. So we'll substitute all the values of mu, W, R, and alpha, and the frictional torque comes out to be 43.3 Newton meter according to uniform wear theory. Okay. Again, for calculating the power, we'll substitute T and W, and it comes out to be that the power loss due to uniform, as per uniform wear theory, is 634.8 watts. Okay, so the numericals are again very straightforward. If you know, if you write the given data properly and know the formula, uh, then you can easily calculate it by keeping all the values in SI unit. Okay, so I hope this is clear to you. Now let's move on to next numerical. Before going to next numerical, let's just see this trapezoidal or truncated conical pivot bearing. So what is the difference? It is very similar to conical pivot bearing. The only difference is this cone, this shaft is not made pointed as we saw in the conical pivot bearing, but it is stubbed from the top. Okay, so there is this flat surface which is generated in case of trapezoidal or truncated conical pivot bearing. Okay, so there is this flat surface. So if you see the top view, you will see two circles again. So this first circle, this inner circle is having radius R2, and this outer circle is having radius R1. Okay, and this once we derive it, its expression for frictional torque comes out to be very similar to thrust bearing and conical pivot bearing combined. So this effective radius R effective is very similar to thrust bearing, that is R1 cube minus R2 cube upon R1 square minus R2 square, and this cosec alpha has to be multiplied over here. Okay, again this alpha would be the semi-cone angle, right? And this cosec alpha will have to be multiplied. So this is the expression according to uniform pressure theory. And again, according to uniform wear theory, this frictional torque would be 1 by 2 mu into W into R effective multiplied by cosec alpha. And that R effective will be R1 plus R2. Okay. So if you have studied thoroughly the uniform, uh, if studied thoroughly what? Flat, thrust bearing, that is collar bearing, and conical pivot bearing, then you can easily write the expression for torque using uniform pressure theory and uniform wear theory. Okay, so it is very straightforward. Now let's quickly understand this with the help of a numerical. All right, so a conical pivot supports a load of 20 kilonewton. Okay, so the value of W is given to us. The cone angle is 120 degree. 2 alpha is given to us. The intensity of normal pressure is not to exceed 0.3 Newton per mm square. So the normal pressure in case of conical pivot bearing, we saw that it was in uh, it was the Pn, the value of Pn, which is the normal pressure, and this normal pressure was perpendicular to the this conical surface, right? So this is given to us as Pn as 0.3 Newton per mm square. So the value of Pn is given to us. Now the external diameter is twice the internal diameter. So it is not mentioned as truncated or trapezoidal conical bearing, but since it is asked, it is given the relation of internal and external or inner or outer radii is given to us. So we can clearly assume it as we can we know that this is the question of trapezoidal conical pivot bearing. Okay. So the relation between R1 and R2 is given to us that R1 is equals to 2R2. Okay. Now what we have to find is the outer and inner radius of the bearing surface. So R1 and R2 we have to determine, and the relation of R1 and R2 is given to us. If the shaft rotates at 200 RPM, so N is given to us, and coefficient of friction is given to us. Find the power absorbed in the friction. Assume uniform pressure theory. So according to uniform pressure theory, we have to determine the power absorbed in the friction or power loss due to friction. Okay. Now, first of all, what we'll do is write the given data. W is equals to 20 kilonewton, and we'll write it in terms of Newton. 2 alpha is 120 degrees, so obviously alpha will be 60 degree. This Pn is equals to 0.3 Newton per mm square. N is equals to 200 RPM given to us, so we'll find out omega, and omega comes out to be 20.95 radian per second. And this mu is equals to 0.1. All right. Now, what we have to do is first calculate the inner and outer radius of the bearing surface. So let R1 and R2 are the outer and inner radius respectively. Okay. And this relation is given to us. R1 is equals to 2 times R2, right? So this equation for Pn can be written. This Pn pressure is nothing but load upon area. And this area would be pi R1 square minus R2 square, right? So this W we can calculate. Okay, R1 and R2 are not known to us. So, but relation between them is known to us. So we'll write, instead of R1, we will write 2R2 and we solve it. And we get that R2 is equals to 84 millimeters. Okay. And we know the relation between R1 and R2. So we'll calculate R1, and R1 comes out to be 168 mm. Okay. Now we know we have to calculate the power which is lost in the friction. So first we have to calculate the torque. Okay. And for uh, truncated conical pivot bearing or trapezoidal conical pivot bearing, we know that for uniform pressure theory, this is the formula. Okay. So we have all the values. We have the value of mu. We have the value of this W is also known to us. This alpha is also known to us, and R1 and R2 have calculated. So we'll put the respective values and calculate it. So we get this frictional torque as 301.76 Newton meter. All right. And once we have this value of torque, we already have calculated the omega. So this omega, so we can calculate the power. This power is equal to T into omega. We keep the respective values, and this power comes out to be 6322 watts. Okay. Or this can be written as 6.322 kilowatt. Okay. So as you can see, these are pretty much straightforward questions. Very simple questions are coming from this chapter, and also the derivation is also very straightforward. Once you understand the diagram clearly, so you need to follow the steps. That is, first we will determine the load coming on the elemental ring, then integrate it in order to get the complete load. Then you will find the frictional force. Frictional force can be determined by multiplying the uh, coefficient of friction in the load. And once we have uh, frictional force, we can determine the frictional torque. Okay. So these are the steps which we have been following in all the derivations. So understand the steps clearly, and uh, remember the diagram which is for every bearing. Okay. So I hope this is clear to you. So in the today's class, we derived the expression for flat collar bearing, and we solved few numericals for conical pivot bearing and truncated conical pivot bearing. Okay. So I'll conclude my session with all this. So thank you everyone for joining. We'll meet in the next class.